Hello guys, in today's video we're going to be talking about variational autoencoders, a foundational model in case you wanted to learn generative AI. So I divided the learning task into three different objectives. First, you should be able to explain how a variational autoencoder works to basically anyone. So you should be able to understand, to explain the architecture, the different components in the architecture, and how basically variational autoencoders are able to generate images. The second task is to be able to understand it from a mathematical point of view and to be able to derive its mathematical equations. This would not only further your understanding of the topic, but also it will help you understand how the network was designed. So it will help you understand the intuition that these two guys, Diederik P. Kingma and Max Willing, had when they designed the variational autoencoders. And last but not least, you should be able to code a variational autoencoder from scratch and train a variational autoencoder network, maybe for your internship, for your job, for your lab. So at the end of the three videos I made, you'll be able to achieve all these tasks. Now for today, we'll be focusing on understanding how variational autoencoder works, its different components in its architecture, the loss functions, and basically how it's able to generate images. So without further ado, let's get started. So what I usually recommend when you're learning any machine learning architecture is to go and read the original paper. That's one. So read it and really understand it. And two, code it from scratch. And this will really increase your skill level. And that's what we're gonna do in the next videos. So we're gonna read the original paper, Autoencoding Variational Bayes. It was co-authored by this guy, Diederik P. Kingma. And if you're not familiar with this guy, he's the guy that came up with the Adam optimizer. So he's really famous in the machine learning realm. So before reading the abstract, let's go over a few stuff first. First of all, what's generative AI? Generative AI is a deep learning realm that deals with the generation of objects. Now, the objects can be basically anything. They can be images, they can be videos, they can be audio, but in most cases, they are images. So if you're applying for a job, maybe it's a generative AI internship or job, it may be corresponding to the generation of images in most cases. And recently, video generation became really popular, especially in the last 2 years. But when you really understand how you can generate images, migrating to generating video is really easy because the video is basically a collection of images. So let's go over what generating images really mean. When I'm saying generating images, it's basically meaning a network that can create an image. When I say create, it means creating out of nothing. And out of nothing means randomly. Now, a network always needs an input. So when I say randomly, it means that the input should be basically anything, and depending on what the input is, the network should be able to generate an image. Let's say our generative AI network is a network that generates images of cats. So we sample a variable z from a statistical distribution. Let's say z follows a Gaussian a normal distribution of mean 0 and standard deviation 1. So we sample it. Let's say we get a value of 0.2. When we input it to our network that we're trying to find, f theta, when we input z to f theta, the network should output an image x. Now you'll ask, okay, what are the problems with this learning task? Well, let's go over what an image is. Let's say you have an image of a circle. So we have a very small image of a circle over here. Let's say it's of dimension 25 by 25. So to represent the image, we have 25 rows, 25 columns, and each of these has a pixel value. So we have 25 by 25, which is how much? It's 625. So to represent an image of a circle, we need 625 variables. So if we want to make a network that generates images of circles, we're basically gonna have to have the output layer of the network output 625 numbers. Second of all, we're taking the case of a really small image. Let's say we have an image of a cat of really high quality. So let's say it's 700 by 700. And this basically means that we have 49,000 variables to represent the image. So 49,000 variables corresponding to the color of each pixel. So the output layer should have 49,000 numbers. As we can see, it's no easy task. Now, we're gonna see how variational autoencoders manage to do it, and in future videos we're gonna go over how other generative AI models manage to do it. So let's take the case of the circle again in our explanation. So what's the approach that variational autoencoders took? Well, they went over the idea that if you want to represent a circle, you can say, hey, I want to represent a circle of 25 by 25. Can you draw it for me on a computer? I'll be like, okay, sure. Give me the matrix. So you'll give me the color matrix. Let's say you have gray, 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 and then you have a red pixel value. So a red pixel value, and then a corresponding gray, 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 gray. And then you'll be like, okay, I have a red pixel value here, 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 here. And then you'll give me the rest, which are all gray. Okay, so you get the idea. I'm not gonna complete it. So if you give me the value of every pixel, I'll be able to draw a red circle on my computer. All right, but it's too much variables. The very easy intuition is that to represent a circle, we just need two information. Actually, we need three. So we need the center. So where is the center of the circle? We need the radius, and we need the color. So here we have a color red. So we need the color. So if you give me these three information, I can draw any circle you want. And this is the intuition behind variational autoencoders. It's that really large objects of really high dimension, like images, which need 50,000 variables to represent, we can actually represent them in really small dimensions. So this is the main intuition they had. So let's go over the higher picture. So this is a really high representation of the network. We have an input X, all right, of really high dimension. Let's say it's 49,000. So it's an image of 700 by 700. We input it to an encoder, and encoder in English language basically means something that encodes. When we say encode, it means compress, and compress means like shrink. So we're basically decreasing the dimension. So instead of representing X with 49,000 numbers, we represent it in a Z dimension, which is very small, let's say of dimension 2. And usually Z is in a statistical distribution that is simple. And the most common one is the normal law. So that Z would be following a normal of mean mu and standard deviation sigma. Let's say normal 0, 1, for example. So we have an input X. We input it to the encoder, and the encoder would output Z in really low dimension. And then we have a decoder, all right? So we have a decoder, and the decoder in English, it's decoding. So it's breaking the code. So I had X, I made a code for X, which is two numbers that can help me identify what X is. The decoder should be able to take these two numbers and break the code and give me back the original image. So we had X in 49,000. We got Z following a normal distribution of mean mu and standard deviation sigma. And then we input Z to the decoder, and Z would output an image X prime, let's say also of the same dimension, so dimension 49,000. And in an ideal world, X would be equal to X prime as close as possible. So that's how you train a variational autoencoder. So you have an input X, you input it to your first neural network. So this is the first neural network, and it has parameters phi. So it has weight parameters phi. We get a variable Z following a normal distribution. We input it to the decoder, and the decoder should give us back X prime. All right. So this is basically the higher level picture. We're gonna go into more details, but I hope the first idea is clear. Input, really high dimension. First network, we get really low dimension, like a compressed object. Then we input it to the second network, and the second network should give us back our image. So I hope that part is clear. We're gonna go over now like more details as the video goes on. So in the case of circles, we got an input of an image of a circle. Let's say we got, just for illustration purposes, we got the radius and the center. The decoder network should be able to redraw the circle. And this is how variational autoencoders work. Now, in all what I just spoke about, I'm just speaking about the training. So here I'm talking about how you train your variational autoencoder. However, when you're done training and you want to generate images, you basically delete the first part. So this part over here, you get rid of it. So let me just like throw black over it. So in the inference, basically we just got a variable Z. It's inputted to the decoder network, and then the decoder network would generate an image. So Z follows a normal distribution. So Z would be corresponding to a normal distribution, and this is the image of a normal distribution. So we sample from this normal distribution, we input to our network, to our decoder network f theta, and the network will generate an image. So we have two parts. First, we train our network. So we take input, encoder, bottleneck, decoder, output. We finished our training. We don't use the encoder and the input. We just take from here till here. We sample from a normal distribution. We input to the decoder, and for every sampling, we'll get a different image. So it depends. It depends where you sample. Let's say the first time you sampled over here, got a value of 0.23, you'll get an image. If you sample over here, you get a value of 0.1, you'll get a different image. Now, the decoder network is fixed, so the weights are fixed at the end of the training. However, Z varies because it follows a normal distribution. So for every different value of Z, which is a continuous variable, you should be able to get a different generation, a different image. So this is related to the two parts, training and generation. Now let's go over the network with more details. And now we'll go over the variational autoencoder in more details, okay? Because it's still a bit ambiguous. So again, I'm repeating so it becomes more clear in your head. We have an input X. It's inputted to the encoder network. We get a variable Z, and then Z is inputted to the decoder network, and then we get our image, right? Well, not quite enough. What happens is that the encoder network, it doesn't output a variable Z. It outputs two stuff. It outputs the mean, because I said Z, it follows a normal distribution, right? I said Z follows a normal distribution of mean mu and standard deviation sigma. So for every input x, the encoder should output the mean and the standard deviation. All right. So this is what's written here. We have an input x. The encoder outputs the mean mu and the standard deviation sigma. These are used to calculate z. Then z is inputted to the decoder network, and the decoder network generates an image x prime that should be as close as possible to x. I'm speaking about the training, all right? I'm not speaking about the generation. Now, the idea is that you'll be like, okay, it outputted the mean and the standard deviations, then we use them to calculate z. Why don't we just output z? So if we go over the abstract, in the abstract, basically they say that our contributions, we contributed to two main stuff. The first one is the reparameterization trick. The reparameterization trick, I'm gonna go over it with way more details in the second video, but basically the reparameterization trick is that z should be random. And because z is random and it's outputted by a network, this creates problems, especially in the weight updates, because we have two neural networks and we need to update their weights. So if we're outputting a random variable, so the network is outputting something new every time, that will create a lot of problems when we try to derive the loss with respect to the weights. So we have a network, and the network is stochastic. A stochastic network is a network that generates something new every time. Updating the weights of such network, because it should have stochastic weights, is simply not possible. And this will become way more clearer in the second video, but this is the reparameterization trick. So the reparameterization trick is basically, they said, all right, we outputted the mean and we outputted the standard deviation. Then from outside the network, we sample randomly from a variable epsilon, and epsilon follows normal 0, 1. So this is outside the network. So this is just a variable. We're just sampling from a normal distribution. And this variable is stochastic, it's random. This variable is random. Because this variable is random, whatever the network outputs, so it outputs a fixed mean and fixed standard deviation for a fixed input, even though for a fixed image, so let's say it's this image, it outputs a mean and the standard deviations that are fixed, z would be different, because z is calculated as follow. Z equals to the mean plus epsilon times the standard deviation. So the mean is fixed, right? So for a fixed image, let's say we have this image over here, the network will always output the same two vectors. So it will always output, let's say it outputs 0.1, let's say it outputs a mean of 0.1 and a standard deviation of 0.5 for this particular image. And let's say if we input an image of, I don't know, a sad face, okay? Let's say the network outputs a fixed mean of 0.2 and 0.6. So for this cat, we get 0.1 for the mean. And for the standard deviation, we get 0.5. And let's say for the sad face, we get 0.2 for the mean and 0.6 for the standard deviation. The reparameterization trick is that even though these two are fixed for a fixed input, z is not fixed. Z differs every time. So let's say the first time we sample epsilon. So as we said, epsilon follows normal 0, 1. We sample it and we get a value of 1. In that case, for the image of the cat, the first time when we had epsilon equal to 1, we'll have 0.1 plus 1 into 0.5, we'll get a z of 1.5. Let's say we use the same image again. So we input it to the network outputs 0.1 and 0.5. Even though it outputs the same, Z would be different. Let's say this time when we sample epsilon, we get a value of 0.5. Because epsilon equal to 0.5, we'll have 0.1 plus 0.5 into 0.5, which is 0.25, will get a value of 0.35. So z this time around would be equal to 0.35. And 0.35 is very different from 1.5. So as you can see, for the same input, we're getting different outputs. And this is a stochastic variable. So we made z a random variable, even though the network has a fixed output. So the network has a fixed output, but because of the reparameterization trick, we were able to make z different every time. So we can, in this case, we can use the same input of this image of the cat. The first time we'll get a z of 1, let's say. The second time we'll get a z of 1.2. The third time we'll get a z of 1.5, even though the encoder network is outputting the same value every time. So every time, let's say it's outputting a mean of 0 and the standard deviation of 1. So every time it's outputting a mean of 0 and standard deviation of 1, but z is different every time. And that's because we're following the reparameterization trick. Okay? And then we have z, we have our z vector in lower dimension. We input it to the decoder network, and the decoder network is also fixed, so it's not a random network. It output for a fixed input, it outputs the same, and the goal is to make this output image x prime as close as possible to x. All right? So when I say network, I mean a fully connected neural network. So here we're going into the more advanced territory. But here let's go over again the reparameterization trick one last time. So we have our input x. We input it to the encoder. We get the mean and the standard deviation. We sample epsilon from 0, 1. We calculate z. Z is random. Then we input z to the decoder. And the decoder outputs x bar, and x bar should be as close as possible to x. As you can see, x bar is a bit blurry, so it's not identically equal to x. Now, when I say encoder network and decoder network, I mean a fully connected neural network, like the one shown over here. So I'm talking about a fully connected neural network, all right? So this is the encoder. It has 2 hidden layers, for example. This is the encoder, usually labeled as Q-Phi. Q-Phi is just a convention, okay, guys? This is the decoder, okay? Usually called P-Setta. We input the image. Here it's represented with just 6 variables, but usually it's way higher dimension. We get, let's say, a mean vector of 2 variables, so mu1, mu2, a standard deviation vector, sigma 1, sigma 2. We sample epsilon from a normal distribution, and we use epsilon to calculate z1 and z2, which is the latent distribution. So we went from a dimension of 6 to a dimension of 2, okay? And then z is inputted to the decoder network to output x bar. And the decoder network is also a fully connected neural network. And we have weights over here. So this should have a weight w11, it should have w12, etc. And we have weights over here. Now, usually because we label this one as Q-Phi and this one as P-Setta, is just to show that these weights are different from these ones. So usually we call this one Phi11, it's just like a notation, Phi12, blah, blah, blah. However, these ones over here are usually called Setta11, Setta11, Setta12, blah, blah, blah. So instead of using W, we use Phi and Theta. It's just a convention. However, there's something that I didn't really discuss. I said, okay, so Z is a random variable. It follows the normal distribution. And the encoder network is basically predicting the mean and the standard deviation for this random variable. Why do they do the reparameterization trick? Why don't they just output Z? It's really explained way more in the second video. like the mathematical perspective. So the mathematical perspective is mainly done to make you understand why did they do the reparameterization trick, why their contribution is so important. But basically, like very briefly, it's to allow gradient descent, to allow the gradient flow. Because if we have a network that is random, so every time it outputs a new variable, this network, first of all, I don't know if it exists. For my knowledge, for the best of my knowledge, it doesn't. But this network, we can't apply gradient descent, so we can't apply derivatives on such a network. All right, guys? This is mainly the idea. So this allowed the update of the weights. So phi11, phi12, theta11, theta12. All these weights are updated mainly using gradient descent, like the derivative of the loss with respect to the weights, mainly because we do the reparameterization trick. Okay, so we're done talking about the architecture. Now we have to go over the losses. So any neural network, it uses certain loss functions, and these loss functions allow the neural network to learn and to update its weights. So we reached the final part related to the losses. So it's the losses that our model uses to update its two networks, encoder network and the decoder network, while preserving its goals. So what are the goals that we're trying to achieve? First of all, we have the reconstruction loss. And basically, we want a perfect reconstruction. So for an input image mapped by the encoder to Z, we want our decoder to take this Z and generate an image as close as possible to the input image. So if we take this example over here, so this is the original image, X. This is the generated image, XG. As you can see, this one is a bit blurrier. We want XG to be as close as possible to X. And the simplest way to do that is to simply subtract pixel by pixel. So yeah, that's it. So the reconstruction loss is simply the mean squared error between the original image and the generated image. Now for the KL divergence. What's our goal? So as a reminder, we have our input image X, we have our encoder network. The encoder network predicts a mean and a standard deviation. And the mean and standard deviation are used to calculate Z, and then this Z would be used by the decoder to reconstruct the image XG. So, let's say our mean is very, very big. What would happen? As a reminder, this is during training. So, after we finish training, when we want to generate images, we don't really use the encoder, we just use the decoder. So let's say in our generation, we take a Z, we sample it from N01. So let's say we get a value of 0.65. This 0.65 is injected to the decoder, and the decoder would generate the image. So let's say that the encoder, we didn't penalize means and standard deviations. So the encoder learned to predict whatever mean and whatever standard deviation he wanted. Let's say he got a really big value of mean. Because the mean is too high, let's say 5, Z that the decoder would learn from during training would range between 5 minus standard deviation and 5 plus standard deviation on average. So let's say it would be between 4.2 and 5.8. So the decoder would learn using Z values between 4.2 and 5.8. So when I sample during generation following N01 and get 0.65, he didn't, like the decoder didn't get updated according to it. And because he didn't get updated according to this value of 0.65 would just generate nonsense. For example, it would generate a very blurry white image. Okay? So we can't really have a big value of mean. And actually we want like, sorry, this is the mean. Actually, we want our mean to be predetermined, kind of. So usually we go for a mean of 0 to have it centered around the origin. So this is our first goal. We want our mean to be as close as possible to 0. So let me delete here. We want our mean to be 0. Now for the standard deviation, let's say we did get a mean of 0. If we have a very big standard deviation, what would that do? Let's say we get a standard deviation of 5. So this would be our normal low. So this is -5, this is 5. And for every input image, we would go to somewhere over here or over here or over here by the encoder, and then the decoder would take these values and map to a generated image. So as you can see, the decoder has a very big range to learn from to generate images. And because we have a very big range, we have discontinuity. So let's say one image may be at the 4.2 and one may be at the 4.5, and in between maybe no images of the training dataset would be mapped. So the decoder never learns for 4.3 or 4.4. Would this mean it wouldn't generate? It would generate images. However, they would be like an interpolation between the image at 4.2 and 4.5. So let's say at 4.2 we have an image of a circle, and at 4.5 we have an image of a square. Because we got 4.35, let's say, during generation, the 4.35, which the decoder didn't learn on, he would interpolate between the 4.2 and the 4.5, and we would get like a circle which looks like a square. Okay, so I hope you get the idea. Now, in the case of training data set of cats, we would get like a cat that doesn't really make sense because we have discontinuity. So we can't really have a big standard deviation. Now what happens if we have a very, very small standard deviation? Let's say our standard deviation is 0. So our normal distribution would be just like 1 point. So for every image, we would map it to the same point. And because we're mapping it to the same point approximately, the decoder would just learn from this point. Now, during generation, let's say we sample and we get 0.5. 0.5 isn't this point, and because it's not this point, the decoder would just generate nonsense. Now let's say during generation we did get this point. Because we did get this point, you would say, okay, it'll generate. Actually, it'll memorize the training data set because we are mapping to the same point and we managed to get it. So the decoder would just output a point from our training dataset. So mapping to the same point is bad. Actually, we do want like a bit of discontinuity, but we want the discontinuity to be so small. So let's say we have this normal distribution. We want our training points to be very, very close to each other. So not too far. In the case of standard deviation that's very high, we would have them too far. We would have very big discontinuity in between. And so the model would like output blurry images. And if the standard deviation is too small, we would have like kind of the model would learn to memorize the training data set. So we want our standard deviation not to be too big and not to be too small. So usually we go for a standard deviation of a value of 1. The value of 1 solves it. So we would have like a bit of discontinuity in our training. So the encoder would map the training data set, but like there will be like very small gaps in between. So we would the decoder wouldn't be memorizing, and at the same time it wouldn't be too scattered. And when it's too scattered and we have big gaps, we would have bad generations. So how can we do that? We use the KL loss. And the KL divergence basically it measures how two Gaussian distributions are far away. So let's say we have this Gaussian distribution, and let's say we have this one. So as you can see, they are really close. So they have similar means and similar standard deviations. So the KL loss would give a value of 0. However, if they're too far away, so let me draw in a different color, let's say in black. Let's say this is the second one, so let's call this one P, the blue one let's call it Q, and the black one let's call it I don't know, P, Q, and Y. Okay, so P and Q would have a KL divergence close to 0 because they're really close to each other in mean and standard deviation. However, P and Y would have a very far, they are very far from each other, so they would have a KL that's close to 1, because the KL divergence is between 0 and 1. If they're exactly the same, it's 0. If they're really far away, it's 1. So we usually use the KL divergence, and we make our encoder, because the encoder, as a reminder, the encoder would get us a Gaussian. So we want our Gaussian from the encoder to be as close as possible to a normal distribution of standard deviation of mean 0 and standard deviation of 1. So we want our encoder Q to have a mean mu close to 0 and standard deviation close to 1. So we use the KL divergence. The KL divergence has a very complex mathematical formula. We'll see it in the mathematical derivation video. It's integral over all z of p multiplied by log p over q. However, so I'm not gonna write it here. In the paper, they prove that you can approximate it by summation of mean squared plus standard deviation squared minus log of standard deviation squared minus 1. And so voila, that's it. So this is our network. We predict mean and standard deviation. Let's say we get a mean of 1 and the standard deviation of 0.5. So what we would do is that we would put half into the mean predicted, which is 1 power 2, plus log of the standard deviation predicted power 2, minus the standard deviation predicted power 2, minus 1 standard deviation. So it's just a summation of this. And at the end, we add the two loss terms. And after we calculate the loss terms, we update our two networks. So we derive it with respect to the network of the decoder. The loss, I mean, we update to weights. Then we derive the loss with respect to the weights of the encoder, and we update to weights. And that's it. If you have any questions, guys, feel free to ask them in the comments, and I'll link my LinkedIn. You can send me a message and ask it to me there. And I hope you benefited and understood how generation works. See you in the mathematical derivation video, and don't forget to check out the video of the implementation. See you next time, guys. Bye.